So I want to reference something again we did at the top. I want to thank everybody here for being present for this amazing event we did here online. We got a couple hundred folks up there, so thank you all for being here. We are so excited to present this to you anywhere you are in the world. Thank you again. Thanks to all of you. So another round of applause for our audience. Come on, yeah. Now, as we start the next half here, our next talk is going to metaphorically and possibly quite literally launch us into the next part. The question for you all beforehand: who here is afraid of failure? We got some honest folks, I am too. Afraid of a project going wrong, not quite making the mark. See, and I understand, trust me, I'm up here doing this, I get it. So the interesting thing is our next speaker isn't. In fact, many researchers and engineers you speak to would say quite the opposite. Failure isn't the end of a project or something to be afraid of. It's something to help push it further, educate you. To help drive that point home, we now present and welcome to the stage Dr. Richard Beblo in his talk, Groundbreaking Innovation at the Speed of Failure.
So about a year and a half ago, I was part of a team developing an articulating missile. Spring 2022, we decided to test our design with a sled test. This particular articulating missile, just aft of the head was a joint that allowed the missile to look around while it was tracking targets in the air. And a sled test is exactly what it sounds like. We take the test article, we strap it down to a carrier sled, mount some really big rockets behind it, and fire it down what is essentially a railroad track. So we're at the sled track at Eglin Air Force Base in Florida. It's warm, it's sunny, there's a few clouds in the sky. It is a perfect day for a sled test. And we're standing on the roof of the control tower watching all of this happen. The control tower is a small two-story building, a couple hundred yards from the starting line. So it's time. We light the rockets. It goes screaming down the track. We feel the compression wave hit us as it breaks the sound barrier. And the head falls off and goes sailing over the top of the target at the end of the track. Fantastic, right? So a few minutes later, the track facility manager comes up to the roof where we all are, and he dismisses everyone who's not a lead on the program, which is not normal. So it's just the four of us standing there alone on this rooftop. And he comes over to us, and in his most solemn tone, he says, "I am sorry, we have had an unexpected event." And our reaction to this was, "Oh my God, I know. Did you see how far it went? That was so cool." Just exploding with excitement. And he just stands there and stares at us, wide-eyed, just dumbfounded. He didn't understand how we could be so excited. He didn't get it. And that's what I would like to talk to you about today, why we were so excited to fail. My name is Dr. Richard Beblo. I'm a research engineer here at AFRL in the Aerospace Systems Directorate, and I have built my career on researching and designing morphing structures. Morphing structures being systems that can adapt to changes in their environment to optimize their performance, like morphing missiles, articulating missiles. Dwight D. Eisenhower, commander of the Allied forces in World War II and one of the architects of the invasion of Normandy, D-Day, famously once said, "In preparation for battle, I have always found that plans are useless, but planning is indispensable." One of the greatest military strategists in modern times said, "Plans are useless." What he meant was nothing ever goes to plan. But if you're going to succeed, you need to be prepared. And planning is how you prepare. Plan for success, but be prepared for the inevitable. This perspective applies to developing new technologies. We need to test new technologies earlier than we think we're ready to for the potential to learn. And when we do that, failure is not an event. It's a perspective. Failure is not an event. It is a perspective. When we learn to anticipate failure and not fear it, to use it as a springboard to learning, we will achieve success faster. Everybody wants to achieve success faster today, right? Transition technology faster, be agile, be responsive, move to the next step in the process faster. From a technology development perspective, this directly correlates to accepting more risk. And when you accept more risk, the probability of your missile experiencing an unscheduled disassembly naturally increases. But it's been shown over and over again that the quickest path to success when you're doing difficult tasks is to fail fast and fail often. Fail fast and fail often, meaning build and test as early as you can, knowing it might not work the first time. But if we wait until we are 100% sure our design's going to work, we've waited too long. There's no better example of this than SpaceX. Right? SpaceX has a goal of making spaceflight cheaper by reusing booster rockets. And a few years ago, they set about the task of learning how to autonomously land them. And they failed, and failed, and failed. Until December 2015, they did it. And they did it sooner than a lot of people thought possible. But what if you don't? What if you don't accept this perspective of fail fast, fail often? Well, if you're doing something truly revolutionary, you run the risk of failing late. What does that look like? It looks like this. Do you recognize this data? The red data points are failures. The green data points are successes. Almost every engineering student on the planet has seen this data. We use it in statistics classes to demonstrate the inevitable effect of extrapolating, meaning trying to predict an event outside of the data that you have. In this case, predicting what happens at x equals 31. So if we did a test at x equals 31, would it be a success? The x-axis represents temperature in Fahrenheit at launch, and the y-axis is the number of booster rocket O-rings that show damage upon inspection after recovery. I'm sure by now most of you have recognized this is the data that NASA had prior to the Space Shuttle Challenger disaster. NASA's booster rockets had never been given the opportunity to fail. This highlights three truths. One, the longer you delay testing, the longer you delay critical opportunities to learn. As engineers, we like to admire our problems as we drive towards perfection. But often, testing an 80% solution is a faster path to success. Two, late failures have long-lasting impacts. Early failures can be corrected. Test as early and as often as you can and embrace the risk because of the potential to learn. And three, the risk stays the same. The probability of failure stays the same. The cost increases with time. In the case of Challenger, the ultimate cost, making unexpected events less tolerable with time. NASA's risk tolerance has never been the same, after Challenger. Fail fast, fail often. So, you do a test, and it doesn't go to plan, then what? Standing on top of the control tower in Florida at Eglin, when we saw the head get ripped off of our test article, we were excited because we knew the test just gained value. We knew we were about to learn things that we hadn't even anticipated as things we needed to learn. Everything had more value. The data we collected had more value. Our observations had more value. The test had more value because we needed it to do root cause analysis. The amazing thing about root cause analysis is it is incredibly freeing. There are no bad ideas. The head fell off the test article. It doesn't get any worse. Everything is on the table, right? What happens if you hit the thing with a hammer? I don't know. Try it. So we did, and it made a dent. Great. Now what? We looked at all the data we collected, made a series of plausible explanations that would explain our observations, and then systematically started to fill in the gaps, right? Experiment. What happens to the status lights when a control board loses power? What happens when a breaker trips? How much friction is there if the skin gets pushed to one side? And in doing this, we not only determined what went wrong and how to fix it, but also what almost went wrong, and took steps to mitigate those risks too. Often when people do root cause analysis, they'll do what's called the 5 whys, which is part of the Toyota production system, which postulates that to get to the root of a problem, you have to ask why 5 times. So, why did the head come off our test article? Well, because the aerodynamic load was too great. Why was the load so high? Because the articulation system articulated the nose too high. Well, why did it do that? Because the rotor, which is part of the actuation system, didn't operate as expected. Why didn't it? Likely, it had insufficient power. Well, why didn't it have enough power? Likely, a breaker tripped, isolating one of the 2 batteries that powered the actuation system. It was likely a faulty breaker, which was correctly spec'd and should have been fine, but failed anyway. And in doing so, highlighted a weakness in the robustness of our design. So, moving forward, what can you do? If you are developing the next cutting-edge technology or helping your daughters with their Common Core math homework, if it's your first time, the purpose, the expectation is to learn. And to do that, you need to do 3 things. Okay? First, have the right perspective about your goals. For us, for the sled test, it didn't really matter what happened. It was the first time anyone had ever tried to do what we were trying to do. What mattered was we got the data we needed to figure out why what happened, to learn. 2, have a plan for success. Now, to be clear, I am not advocating that everyone take a Edisonian approach to problem solving, meaning randomly try things until they work, or take on an unreasonable amount of risk. That's a horrible way to do research. Take risk, but calculated risk. And to the best of your knowledge, it should work. But it's research. Understand that your knowledge is limited. And 3, be prepared for the unexpected. Take data, observe, have scripts ready to go so you can analyze data real time while the test is fresh in your mind. Set yourself up for being able to do root cause analysis afterwards. It doesn't matter if you're doing a benchtop test, or a full-scale rocket test. Always do quality engineering and let the lessons of test boost progress. Because the only failed test is a test you didn't learn anything from. So, back to our sled test. We did exactly this process of going through root cause analysis, identifying all the issues, proposing solutions. And soon, we're going back to Florida to do another sled test with an entirely redesigned test article, incorporating all of the lessons learned from the first test. And we plan to succeed. So remember, failure is not an event, it is a perspective. The quickest path to success is often to fail fast and fail often. And if you have the right perspective, a good plan, and are prepared, you can't fail. It's only a matter of time before you succeed. Thank you. Have a fantastic day.
Now, as we saw, that program Richard he was working on Mutant. I mean, to see what's happened there, to see that his team is able to innovate, work, and take what they've learned to the next sled test, I mean, we know it's going to be a success, right? No matter what happens. So another round of applause for him and his team. Amazing work, amazing work. Now, like some of you out there, when I hear the word mutant, it brings me back to my childhood, thinking about comics and movies. I'm talking about X-Men. Any fans out there? There we go. Yeah, I'm more of a cable guy myself, but love them all. That said, the thing about X-Men that always comes to me is the idea that our differences. People may point out thinking we're different because we're failures. We're not. We're made better for it because of what makes us different. And that show and that series really proves that point.